Today we covered those in detail, and we'll see the topic first. We'll have a basic understanding about it, and we'll proceed to implementation afterwards. So we'll start with Preorder Traversal with groups.
Okay, so from the three traversals that we're going to see, the algorithm of Preorder Traversal is first we process the node we're in, which is at first what is the reference of the tree? What's the reference of any tree? It's the root, right? So first we traverse the root, and then we do the same thing to the left subtree, and then do the same thing for the right subtree. Is that clear? So if not, okay, let's do it more. So think of it as so doing the, let's see this example. The root is 1, so we do processing with 1. In our case, let's just say it's printing something. So we process 1, and then the left subtree gets the same recursive definition. So for the left subtree, what's the root? 2, right? So we print itself, right? Like we process it, and then this calls the same thing for the left subtree, right? So what's the root for the left subtree of 2? It's 4, right? So 4 gets processed. So after this, 4 is the leaf of a tree. So getting back to 2, and then after calling itself, and then its right subtree, what does 2 call? I mean calling its left subtree, it calls its right subtree, right? So for the right subtree, what's the root? It's 5. So 5 processes itself. In our case, it's printing it, and then it's done. So at this step, this subtree is done. So what did 1 do? 1 processed itself, and then its left subtree. The left subtree is done, and then it calls the right subtree. So what's the root in the first right subtree? It's 3. So 3 processes itself, and then calls its left subtree. It currently doesn't have one, so it calls its right subtree, which is this. So 6 processes itself, and then it calls its left subtree, and then 7 is a leaf node, and then it calls its right subtree, but it doesn't have one, so we stop there. The reason I'm saying process is we don't know what we're doing, so that it depends on what we're trying to achieve on each level of the tree. So in our case, just say we're printing it. So our preorders goes something like this. So when do we use preorder? We use preorder traversal when we want to process the value first, and then its left subtree, and then its right subtree. So yeah, that's the use case. First, let's do it recursively because it seems easier. We all can participate in doing it. You can pitch ideas, and then we do it iteratively. It's not like we're trying to make it harder. It's a real thing. You get asked do it recursively and iteratively questions, and since this is a more famous question, it might not be this, but you would get a hang of solving this kind of questions. So let's do it recursively first, and then do it iteratively the second round. So who wants to talk on the recursive part? It's random ideas. It doesn't have to be so organized. Any ideas? So okay, in that case, let's follow how we solve a recursive function. So you can pitch on the steps. So what's the first step we need for solving the recursive function? Base case, yes. What's our base case? Speak up.
The root. If you don't have any right or left child, it would be
If it's none,
Yeah.
we don't do anything, right? So none, let's say it returns. And then what are the recursive problems or the repeated iterations that we do here? Let's say, so what do we do? First we process it, so it's right. In our case it's printing it. So the recursive problem. So what do we do first? Do we do that first? 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 Print it. Because we process the itself first. Does that mean? So we print itself. Let's say we have the root. So let's say we have a node. So it prints itself, and then what? And then what? Do the same thing for and then okay, and then
Also do the same to the right.
Okay, so this is the pseudocode. Are you? Do you have a confidence to implement it in your own language? If you have any doubts, just raise your hand, and then otherwise we could jump into implementation. So we do 5 minutes for this, and then we can jump into the iterative part. Is that okay?
Just before we jump into implementation, can you also show us like what is happening in the call stack? If we
Oh,
decide to
sure.
run this recursive function? Thank you.
Sure, okay. So we can go over the pseudocode to do this. So assuming we have that as an example, first, let's say this function is called with the root 1. So it's not none. So we print it. Let's go over it one more time again, I guess. And then since it's not returning anything, it still exists in the call stack. The null, I mean. Let's say it's a function that accepts the null. And then so we do the same for the node left. It's like the function, when the function is called, it gets to, the next node also gets into the call stack. Node 2, right?
This is our function. Is it the same or not?
I'm just saying it's
Maybe
called
let's
with this
name our function.
argument. It's the arguments that I could have used the function here. I'm just using okay.
Okay, good. But basically here, is everybody comfortable with what is call stack? Like what do we call as call stack and what is the purpose of it? Can anybody tell? It's okay to make a guess. Anybody wants to give it a try? Yes.
A call stack is when you call a function, it's when you call a function, we put our local variable instead of the call function in the call stack. So each time we recursive call, we create a new call stack for that function.
Or any record in the call stack.
Yeah, anyway.
Yes, so basically we keep track of our function's current state in the call stack. It's called call stack because every time we make a function call, it creates a record in the stack. So at the beginning, let's say we started from main, right? And we can say that at the bottom of our call stack there will always be main. Like whatever is our start point, because everything is going to finish execution and return from there, right? We can think of this as is. And once we do our calls to the function, like the reason I asked kiddos to refer with the function name is since it's call stack and function calls are going into it, it's better to represent this with the name of the function plus the variables that are defining the state of a function, right? So what variables are defining a state of a function? You mentioned some of them. You said local variables, right? What else? Arguments, right? The parameters. They are also they can be deciding on the state of the function as well. So this all information, it will be kept and put into the call stack. Like when we are talking about recursion, sometimes we pretend as if like there is magic happening, right? We are like, oh, don't worry about calculating these smaller sub-problems. They are going to be solved anyways. But indeed, in the computer, there is no magic, right? All the calculations are done one by one. And when we do the processing, which element do we process in a step? The top one, right? The last one that was introduced to the stack. So here, for this problem, like once we add our elements, which ones are going to be processed the first unit? By processed, what I mean is it's going to be removed from the call stack. Like its processing is going to be finished and it's going to be removed from the call stack. Which type of nodes are going to be removed from the call stack the first?
None.
The leaves, right? Yes, because we are going to go down till the leaves, and the leaves, they are not going to be able to make any other calls. So do same for node left and node right would not work. Therefore, it's going to reach to the end of the calculation and will return. So thank you very much, Kitos. Now I can we continue with the call stack simulation.
Sure. Okay. So for 2, we print it. That's the first thing we do. And then, obviously, we're checking the if it's not. So we do the same. Do same for node left. What's node in our current state? 2. So 2 left is 4.
I think we forgot printing.
We did it. Okay. So we check if it's not, and then the first thing we do is printing it, and then we call it with node left right. What's node left right now? None, right? And then we check if it's none. If it's none, we return. Since we're not doing something with the returning values, we just return none. It's the same thing here. Since we didn't write anything explicitly, we're just returning none at the end. So I won't write it. So when the function returns, it gets popped out from the call stack. So we get back to the previous state where do Sam's state is talking about a node value of 4, right? So we have already processed this. We have printed this. So when it reaches to here, we have done this, printing it, and then we processed its left. What is left? Processing the right value, right? The right subtree. So what's node right now at 4? It's none, right? So do same none, and then it gets the same thing as the left subtree. It gets popped. So we did this. After this, we're returning none implicitly, right? So this gets popped out. So which 2 operations have we already satisfied or done for this function? Nothing. Which of these 2 operations have been satisfied for the node 2 or this subtree? we currently finished 4, and then we got back to the state of this function, right? Okay, bro.
The printing part and the node left part are all done. So we have left only node 5.
Right. So what do we do right now? What gets into the call stack?
5.
So it's not none, so we print it, right? So it's 5. And then we do same for node left and node right. I don't want to repeat it since they're none. They just go in and then get popped out. Is that clear? Okay. So we have already done everything for 5, and then it gets popped out. So for 2, which of these operations haven't been done? All of them has been done, right? We did the left and we did the right, so it returns something none here. So it gets popped out. And now we're back to 1. So we did print it, and then we did the recursive call for the left subtree. Now we're left with this. So we do same with none. What's the first? Okay, it's right, so it's 3. Sorry, right? So and then we print it, and then we do same for none, right? Since left child of 3 is none, and then it returns, so we pop this. Oh, we don't. That's not it. And then from now on, you start, and then you tell me the operations going that way. What's the next step? We currently process the left part of 3, and then it's none, it got popped out, and then
The right part.
what we add it to the stock, right? Do same with 6. Good. And then it gets into the stack after being printed, and then it's up. After being printed, right? Or we just, oh sorry, and then we added 7 to the stack. So we print it first, and then Sahi. First it gets into the stack resonance, right? And then it gets and then
we put the right child on stack.
what's the right child?
No.
And then no, it's not. It's not. Just the rest.
And obviously
So
we pop out the node.
we
For 3 it's none, so you will pop it up.
for C it's what?
None. You have processed it before.
We have already processed the left and right finger, right? And then it's returned, and then
The same thing. We have already
yes. So that's what happens in the call stack, and then this is our result. I think that's it. So is it okay now to call it, and then do it for 5 minutes max, and then we'll do the iterative thing. It's going to be very similar now that we have already gone through the most cases. So okay, go. Okay.
To the board, please.
So, is there anyone who still haven't done the recursive implementation? Okay. In that case, let's do it iteratively. So, trying to do the recursive part iteratively. For this case, we're trying to simulate the call stack. So, we're gonna use a stack. Thank you. So, looking at the steps of the algorithm, first we're going to process it, and then it's left, and then it's right subtree, right? So, let's assume we add the root of the given tree to the stack. In this case, it's 1. And then we process the left, and then we process the right, right? So what should be added to the stack? What do you think?
Right.
The right? Why?
Because the last element we need to process the left, right? So we need to process the left first. So if you add left in the stack first, we import, we don't list it on the top of the stack, so you push right.
That makes sense. Yeah. Anyone didn't get it? So
Can we have an example of the 3 nodes? 1, 2, 3.
oh, can we use this? So let's assume we're doing this. So the next one we're going to add, let's assume both are unknown nodes. One has 2 children. So the next one, the first one we're going to add after 1 is going to be processed last, right? Because of the property of stack, the value at the top is going to be processed first. So if we had added 2 and then 3, the child that's going to be processed would be the right one and then the left one. We don't want that. Since we're using a stack, we want the left subtree, the node representing the left subtree to appear on top. So we first add the right subtree node and then the left. And then we do the processing when we're adding it means printing. So, and then we do the same thing for 2. Let's assume now we have these 3. So 2 has 2 children, 4 and 5. We add to the stack the right one first, and then the left one, and then we get the left one first, and then if it's none, we don't add it to the stack. So it has only none as a child, so we pop it. If there is nothing to add, we pop from the stack. And then it's 5, nothing to add. And then 2. And then, oh wait. Anyone pointing?
We have to add 1 first, but we have to print whenever we are popping or to stack.
Did you repeat?
We have to add 1 first, and we always add the children of the top of the stack. So in this case, when 3 and 2 were added, one should be there because 1 is popped, and children of 1 will be inserted. But whenever we pop, we insert its children.
Could you go over this the example I just did?
First, we insert 1. The processing we are saying is just printing for now, right?
Yes.
So we we should first insert 1. And whenever we pop 1, we print 1. And we insert the children of 1 here.
Yeah, that
And
makes
the
sense.
right one first, then the left one. Then we have nothing. Then we pop 2. And we insert children of 2. Right
So
one
we
first.
didn't do that cleanup. Yeah.
Yeah, we didn't do the printing in the pop.
Yes. So yeah, that's what we missed. We didn't do the cleanup. So 3 was in the stack. So it gets processed, right? Oh, we missed. Okay, we missed something. We didn't do the things.
We have to add 5 and 4.
Oh, we did them, right?
Okay, okay.
Now we are in the right side. So 3 doesn't have a left child, and then so we don't have the left one. So and then we have the right one. We processed it. And then we add the right one. And then after printing it, we add the left and the right. 7 and 9. If you add, but you don't have to.
And then insert 1.
Yes. So yeah, that's it. The one thing we changed from the call stack is instead of adding the left knot first, we add the right knot in order to access the left one first during the next step. And then after processing it, we clean up the current knot from the stack. I think that's the thing we missed, right? But that's it. If you have any questions before implementing it.
And we process the elements. When we add them or when we pop them?
So you
When we add them or when we pop them?
we mean printing them. Okay, right. Processing the same thing. Does that make okay? I think when you're cleaning up, we proceed to do the left. I think when we're adding them because when we're adding the left ones, because we have to print them before doing the same thing for the left ones.
Since we are inserting right first.
When you insert the right one, you don't have to insert. When you pop one, you're gonna
Clean the roots.
when you
Clean the
pop
pop.
the stuff, you're gonna clean the one, not clean the right one.
I think what don't we print when we're adding the roots? That doesn't it have to be the first one? Why?
It gets popped first since it's the only element in the stack before we started iterating it.
Oh yeah.
So we first
Yeah, that
pop
makes
one.
sense. That makes sense.
Is everyone clear? One more time.
Could you go over sister?
We first insert 1 to the stack and we do our iteration now. Like in a loop or implementation. So we pop 1 first, so 1 gets printed. One gets printed and we insert children of 1 to the stack. But we insert the right one first, which is 3, and the left one second. 2. Now we pop. 2 is popped, 2 is printed, and we insert children of 2. Right one first, 5. Left one next, 4. We pop 4. We print it here. We insert children of 4. We don't have any children, so we can have the check here, and we won't insert anything. Then we pop 5. We are iterating until our stack is empty. Since we have everything, it means we have something unprocessed. So we have 3 now here. We will pop 3 and add children of 3, the right children, 6. And
I think we forgot 5.
we have to insert.
Okay, before writing 3, we hit 5.
Okay, for 2 we insert
5 times 4. Yes.
We put pop 4.
Yeah, we
have
No, wait.
let's start. We pop 1, we print it, we insert children of 1, 3 and 2. We pop 2, we print 2, we insert children of 2, 5 and 4. We pop 4, we print 4, we have no children. We pop 5, we print 5, we have nothing to insert, it's popped. We pop 3, print it, insert children of 3, the right one first, 6, left one, we have no left. So we pop 6, we print it, and we insert children of 6. Right children, nothing, and left children, 7. We pop 7, and we print 7. So we have nothing in the stack, and it's end of execution. Pop, print, insert right, insert left. Pop, print,
The outputs. And it's a preorder. 1 to 4.
Next again.
Sun, then left sub 3, 2, then left, then right, 4, 5. This means we have processed sun and the left sub 3, what's left, the right sub 3. For the right sub 3, we print self 3, then the left sub 3, we have nothing, then the right sub 3. For the right sub 3, we print self, which is 6. The right sub 3, 6. Then the left 7.
So one thing I want to add is all of these operations are super optimized. We can literally try to mimic the call stack. So let's add 1, and then if we remember from the call stack, we don't remove it right after processing it. And then we add 2, and then we add 4, and then if this is our best case or it's not, and then it's a leaf node, we pop it, right? That was what we did for the call stack. But when we return here, we kind of need a way to check if we have processed the left part of it too. So that's what it tried to optimize. So instead of saving a state that showed that the left part of it has been optimized, it tried to pop the root node. So if you want, you can try to mimic the call stack by saving a state if the left part if the right part of it has also been. So in this case, since if we can know in some way the right subtree of this value has not been processed, we can add the right child of it. So let's say this was false first, it had a boolean. That means the right part hasn't been processed. So we add 5 and then makes this true. So the next time we see this element, we are going to pop it, right? That's what we did for the call stack, right? It was 1, 2, 4, and then 4 got removed, and then 5 got added, and then the next time both are going to be popped, right? So in order to remove saving this state, that's what he wanted to show, but you can do it this way. Is that clear?